So yeah, I'm going to begin recording now. Let's welcome Oleg Lebedev, who is a professor at Helsinki Institute of Physics, and he's going to talk about gravitational particle production and Friesen coupling, at stronger coupling today. So please start whenever you're ready.
Yes, thank you. Thank you for inviting me, and in particular, Professor Ko. I'll talk about two sort of distinct ideas. One has to do with gravitational particle production, and the other one has to do with Friesen. And in fact, I'll try to connect them smoothly because the second part of my talk is motivated by the first part. Okay. So here is a list of subjects I'll talk about. So I'll talk about gravitational particle production, and the reason why this is important for cosmology is because it provides an irreducible background for dark matter studies. Because simply you cannot switch off gravity and say that, okay, it's not there. I do my model and that's it. So you really, if you're serious about model building, you need to take into account gravity. So specifically, I'll talk about gravitational particle production during inflation and immediately after inflation, in particular during preheating. Of course, as I said, you cannot switch off gravity, so it's always there. But gravitational effects are proportional to the energy of the system. So when the energy is small, such effects are small as well. So the most important effects have to do with inflation because the energy density is very large, and also during preheating because the uh, there was not enough time for the energy density to get diluted. So gravitational effects are still very strong. You can also go to reheating, but then the such effects are typically much smaller simply because the system has diluted, the energy density has diluted, and the gravitational effects became smaller then. Okay, so and then the second part of my talk has to do with Friesen. So Friesen is one of the standard mechanisms to produce dark matter. But I will talk about the specific realization of this mechanism, which we call Friesen stronger coupling. And the reason why I'm talking about it is because this is a framework which is actually predictive, which is highly unusual for Friesen models. It requires low temperatures, and in fact, it's observable. So the key references are listed here, not all of them, but some of the papers. And then I will quote some other references on my slides. Okay, I guess the way we proceed is that you can interrupt me at any time, maybe raise your hand or something, and I will, once in a while, I will just stop and ask for questions. If that's okay.
Sounds good.
Okay. Yes. So let me start with some very basic remarks, which, however, are not often appreciated. Okay, so dark matter models can be split into two broad categories. One is thermal dark matter, and the other one is non-thermal dark matter. Some very generic classification. So in the first case, you produce dark matter in some way. It doesn't really matter how you produce dark matter, but as long as the coupling is not too weak, the system thermalizes, and the number density of dark matter particles is determined entirely by the temperature, nothing else. So the memory of the initial conditions has been erased. And the system is completely thermodynamic, and so its evolution is determined by the temperature and eventually by the freeze out. So the usual freeze out mechanism, that is, the eventual number density is determined by the coupling between dark matter and the standard model. So in this sense, this class of models corresponds to an attractive solution in the theory space, because no matter where you start, you end up at the same place. So it has no memory. On the other hand, the situation in non-thermal models is very different. So the number density of dark matter particles builds up over a long time, and it is determined by a given mechanism, which you choose by hand. And normally people start with the initial zero abundance of dark matter particles and use their favorite mechanism to produce them. However, this framework as a whole has a feature which is memory. So the abundance of non-thermal dark matter is always sensitive to the way it has been produced and also to the initial conditions. It's just a very generic statement. So it has memory. So if you change the initial conditions, the eventual abundance will also change. So that makes it very different from the thermal case. Now, let me make some more general remarks. So I would say that psychologically, thermal particles are very natural because that's all we observe. Yeah, so the particles we observe in nature are all thermal or have been in thermal equilibrium simply because we only observe particles with large couplings to the standard model. So all of the particles we know have gauge couplings, and that's why we observe them. So they have been thermalized. The second point is that the freeze out is a real physical phenomenon because that's what happens to neutrinos. Neutrinos exist and they actually have frozen out. So this is, again, not some theoretical construct, but this is a real phenomenon that has happened in the early universe. Okay, so we cannot say much about non-thermal particles, though, because the non-thermal particles require a paradigm shift. These are very challenging. There are no really examples of such particles. And as I said before, the initial conditions for non-thermal dark matter or non-thermal dark relics is as important as the production mechanism, unless you prove otherwise. A bigger problem is that gravity is always there. And if you have a specific model of non-thermal dark matter, you must prove that gravity is irrelevant. Otherwise, there is really nothing to talk about. Okay, so what do I mean by gravity here in this specific talk? I will consider two sort of extreme cases of gravity. I will try to explain what I mean. So first of all, gravity corresponds to an expanding space-time background. That's what I mean by gravity in this talk. In particular, the expanding space-time background during inflation is gravity because it corresponds to change of the metric. The metric is gravity. And I will also consider quantum gravity effects, which can be summarized by a set of high dimensional operators that couple everything to everything, and they're Planck suppressed. And you can write quantum gravity effects in this form only after inflation, when the field value of the inflaton becomes small. So a set of Planck suppressed operators will capture some effects, or probably most effects, of quantum gravity after inflation. Now, what I need to mention here is that the graviton exchange is totally inadequate for these purposes. This is a subject of a lot of research. Somehow people assume that if you draw a diagram with a single graviton exchange, you take into account gravity. And this is, of course, is completely wrong. So first of all, if you have a classical background, you need to take into account an infinite number of gravitons. So it's a semi-classical process. So a graviton exchange doesn't work. But then also we know that at high energies, gravity is not classical. It just doesn't work as a classical concept. I mean, you cannot really use even a graviton, most probably as a quantum. So there are various issues, unitarity, non-renormalizability, and things like that. So at high energies, you simply cannot allude to the graviton exchange diagram. Instead, what you can do is that you can parameterize quantum gravitational effects in terms of effective operators. And that's what I will do.
I have a question.
Yes, please.
So, do you also consider the production of gravitons?
No, not in this work. I can,
Mhm.
but for my purposes, it's not relevant because I'm just interested in production of particles which are stable,
Okay,
which are massive, and that can potentially constitute either dark matter or dark relics.
I see. So you only focus on the off-shell gravitons.
Yes, I mean, like I said, so the production of gravitons is not very difficult because often it just reduces to production of massless scalars. So it's not very difficult to take it into account. It's just not needed for my purposes.
Okay.
I will, I think when I proceed, it will be more clear, I hope. Okay. Yes, so let me start with inflation. So here is a cartoon of inflation. So we have exponentially expanding space-time. A is the scale factor. And clearly, intuitively, when we understand this is a very violent, non-adiabatic process, so naturally it leads to particle production. And so the way it can be formulated is as follows. So any light scalar, and light meaning that it's lighter than the Hubble rate. It can be super heavy, but still light compared to the Hubble rate. Any light scalar experiences quantum fluctuations in de Sitter space, which are sort of shown here as a wave. Such fluctuations build up and they carry energy, and after inflation stops, these fluctuations are converted into particles. So that's the way particles are produced during inflation. There are different descriptions of the same phenomenon, but they're pretty much equivalent. So during inflation, all particles are produced because you cannot switch off gravity. So you have a time-dependent background, so it produces everything. And the question is whether it's relevant to any interesting physical phenomena or not. And maybe for many purposes, it's not really relevant. But for instance, for dark matter and dark relics, it is relevant. Now, the particle production process does not stop even after inflation. because after inflation we have inflaton oscillations. The inflaton field oscillates as a coherent sort of classical field, a semi-classical field. And the inflaton field oscillates with a high frequency, which is given by the inflaton mass. And the inflaton mass is typically taken to be heavy. Is not always the case, but normally it's taken to be heavy. So the oscillation frequency is very high. And since you have a classical background that oscillates with a high frequency, you produce particles whose mass is lower than the frequency. Again, this is intuitively clear, and you can show it explicitly. So you produce particles via gravity. You don't need any other interactions, even at that stage. Okay, so let me discuss one approach to particle production. Which is known as the Bogoliubov approach. So suppose we have a scalar field on a de Sitter space, and we expand it in creation and annihilation operators as usual. We assume that the scalar field is free, so there are no self-interactions at the moment or interactions with other fields. So you expand it in plane waves and creation and annihilation operators, and the time dependence is restricted to the functions chi k, the mode functions, and the rest of the factors are time independent. Eta here is conformal time. So these mode functions satisfy the equation of motion, which is written here, where the frequency is given by the three-dimensional momentum, the mass term multiplied by the scale factor, and the coupling to curvature. So if the scale is conformal, this term goes away, but in a more general case, you have a curvature term. So then the procedure is as follows. So you solve this differential equation with this given boundary conditions, and the boundary conditions are set by basically by the flat space boundary conditions. So if you go to very early times, formally minus infinity in terms of the conformal time, your space is effectively flat because the scale factor is small and the momentum is large. So you effectively have a flat space. So the solution is just plane waves with a slowly changing frequency. And the same applies to very late times. So now, so we have effectively flat space because the Hubble rate is very small. So the scale factor is large, but it's changing very slowly. So effectively we are in flat space. So again, we can use plane waves. And so one can build two different sets of solutions to the equations of motion with different boundary conditions. But of course, these solutions are not linearly independent. They solve the same equation. And so one can express the in solution with the in boundary conditions at minus infinity in terms of the out solutions and out complex conjugate with some constant coefficients, simply because it's a second order differential equation with a real coefficient. And so that's how the constant coefficients alpha k and beta k appear. And one can rewrite the initial scalar field in terms of chi in or chi out. And in this process, one has to transform the creation and annihilation operators for the in states into creation and annihilation operators for the out states. So basically, this is just a basis transformation such that the scalar field remains invariant. And so this transformation is known as the Bogoliubov transformation because it mixes, if you look at this, the lower line, this transformation mixes annihilation and creation operators. Okay, so the next step is to define the vacuum. So the natural condition, which is used pretty much always, I think, in the literature, is the Bunch-Davies vacuum. So you define your vacuum as a state which is annihilated by all in operators, because we start with some state in which there are no particles, and then you have a time-dependent background which creates particles, and eventually you can measure the particle number at time plus infinity. Okay, so this is a natural condition, and the particle number at late times is defined using the same in vacuum, but the particle number operator depends on time and is formulated in terms of the out operators, and you can measure how many out particles are contained in the in vacuum. And this is given by this formula. And this beta k is known as the Bogoliubov coefficient, and it can be computed once you solve the equations of motion with given boundary conditions. And so this is the way. This is an example here. So, for instance, if we have inflation followed by the radiation domination epoch, then the particle number is given by this formula. So what you do here is that you solve the equations of motion during inflation and then during the radiation domination epoch, and then you compute the in and out functions. And according to this formula, you compute the Bogoliubov coefficient, and based on that, you compute the particle number, which is given here. And so what you notice here is that the particle number produced by gravity, by inflation, contains a ratio between the Hubble rate during inflation, which is HE, and the particle mass. And so if this ratio is large, the particle number can be enormous. So if you take a typical Hubble rate, something like 10 to the 13 GeV, and the dark matter or dark relic particle with the mass 1 GeV, this ratio is just enormous. Okay, so this just to show you that the gravitational production mechanism is actually extremely efficient. And here is an example of the spectrum. So you compute the Bogoliubov coefficient squared as a function of the momentum. And what you find is that if at small momenta, the Bogoliubov coefficient is basically flat, so you produce all particles with the same occupation numbers. But then if the momentum of such particles is large, if it approaches the Hubble scale, then the occupation number decreases rapidly and you don't produce very energetic particles, which again physically makes sense.
I have a question.
Yes.
Yes. So in this expression, is there any dependence on the parameter psi, which measures the breakdown of the conformal symmetry, and also what happens is if mass m going to zero limit?
Right. So this formula works for minimally coupled scalars.
Okay.
So psi equals 0.
Mm.
But so for a non-minimally coupled scalar with a small psi, you
Mm-hmm.
have a very similar formula, which is in this paper. So we
Okay.
derive the same result for a non-minimally coupled scalar, which is not heavy. Because the
Mm-hmm.
thing is that this formalism, the way I presented it, works for scalars which are lighter than the Hubble scale.
Mm-hmm.
Okay, and if you have a significant coupling, a non-minimal coupling to gravity, that makes the scalar very heavy during inflation
Mm-hmm.
because it creates an effective mass, right? So psi times
Right.
curvature, it means basically psi times Hubble rate squared. So your effective mass is of order the Hubble scale. So
Mm-hmm.
it becomes heavy. However, if the non-minimal coupling is small, which is natural because it can be generated by loop corrections, then you can still use this formalism. So if psi is small, then the particle is still light, and you can derive a very similar formula to this one. Okay. So basically, in this case, what happens is that the power of this m changes.
Mm-hmm.
So some power of m remains, and some other power of m gets replaced with the effective mass, which is psi times the Hubble rate. So it
Mm-hmm.
changes a bit, but not much. So in fact, I will show a
Okay.
formula later on, which
Oh,
is universal.
okay.
And yeah, so but the mass goes to zero limit. Formally here it doesn't work because there are many reasons for it, and one is that there is infrared divergence. So the Bogoliubov approach basically assumes that inflation takes an infinite time, and if you have a massless scalar, it performs a random walk
Mm-hmm.
and it diverges to infinity
Mm-hmm.
as a square root of time. I will comment on that later. So,
Okay.
but this formula is not applicable for massless scalars.
Mm-hmm.
What I need to say is that it doesn't actually mean that there is a physically the massless case cannot be handled. It can be, and
Mm-hmm.
it's not problematic, but it's not interesting in terms of dark matter, yeah, because the
That's
mass has to be non-zero.
that's right. Yeah.
Um, and also the thing is that why in reality there is no divergence
Mm-hmm.
because inflation is finite, it's not infinite.
Mm-hmm.
So in fact, you can derive something similar, a similar result for a massless scalar, but you cannot use this
Okay.
traditional approach. You have to be a bit more creative.
Okay. Thank you.
Sure. Okay, so now what are the issues? So this formalism, you can look it up in textbooks and reviews. There are nice reviews on the subject, but somehow in almost all of the cases I'm familiar with, such expositions are quite idealistic. They always start with this Bunch-Davies initial condition. They always impose the in boundary condition at minus infinity, but that's not what happens in reality. Yeah. So first of all, inflation has a finite duration. The minimum duration is 60 e-folds, so 60 Hubble times. Probably in reality has lasted longer, but certainly not infinitely long. And another important point is that the scalars that we are considering do not start from vacuum, from zero initial conditions. They start from some configuration, which we actually don't know. And the best example is the inflaton itself. So inflation starts when the inflaton has a large, so to speak, vacuum expectation value. So the field average is large. It's Planckian, or maybe super Planckian, certainly not zero. So if the Planckian expectation value is, oh sorry, if the inflaton expectation value is very large, why do we expect other scalars to sit exactly at zero? So it's completely illogical. So therefore, what one should question is the Bunch-Davis vacuum of this condition, which we have imposed on our initial state. And so what it tells you is that the traditional Bogoliubov approach is idealistic and doesn't take into account finite time and non-trivial boundary conditions. It doesn't mean that it cannot be adapted to this case. Of course it can, but it makes the formalism just a bit more complicated. But it can be done. I think it has not been done, as far as I know, properly for generic scalar fields, but it could be done with some effort. Now, what is more convenient for this purpose is another formalism, which is due to Starobinsky, which is often called stochastic quantization. So again, you have the same system. You have a scalar field, which lives on the de Sitter space, that is the expanding universe. And the system naturally has a cutoff or at the energy scale, which separates two different regimes. And this scale is the Hubble rate. So if you have a field, you can always split its wavelengths into long and short compared to the Hubble rate. And that's what Starobinsky did here. So this is the long wavelength part with the long distance, and it behaves sort of like a classical field. And the quantum part contains short wavelengths, and you have the usual creation and annihilation operators. And this step function makes sure that you include only high momentum modes in this expansion. So you can use the stochastic quantization, look at the equations of motion, correlators, and all that. And eventually what you come to is the equation of motion for the field average, or to be precise, for the field average squared. Okay? And this equation of motion for the field average contains the classical term, which comes just from the potential. So this field has a mass, so naturally there is a potential term. But in addition to that, there is a purely quantum term, which comes from the short wavelengths. Okay, so basically we have a classical field, which is kicked by quantum fluctuations once in a while, and the average field changes due to this random force. And the solution to this equation is a random walk. Okay, so here is the average field versus time. If you start from zero, your field experiences quantum fluctuations afforded the Hubble rate per Hubble time, and then you get something like a random walk, and so your field increases over time, and after 60 folds, the average field value becomes comparable or larger than the Hubble rate. Okay, so one thing to remember here is that the field value, the condensate value, cannot be below the Hubble rate. Okay, it can be much larger, but cannot be below, because this is dictated by the equations of motion. Okay, this is the case if you really start at zero. But as I said before, this is extremely unlikely, because, for instance, the inflaton doesn't do that. So why would any other scalar field do that? So what you expect normally is that the scalar field starts at some non-trivial field value and then performs this random walk, not necessarily upwards, but it can also walk downwards. Again, it experiences some kicks of order the Hubble rate per Hubble time. But eventually, at infinite times, it converges to the same value. So basically, there is a critical value or the equilibrium value of phi squared, at which the right-hand side of this equation vanishes. Okay, so this field value squared is basically the Hubble rate to the fourth divided by the mass squared. So the right-hand side vanishes and the derivative therefore vanishes, and asymptotically, you get always the same value no matter where you start. So this is true at infinitely large times. But as I mentioned before, inflation is taken only a finite duration. And so normally light scalar fields don't have enough time to reach the asymptotic value because this process of walking is very slow. For small masses, this term is small. Therefore, normally, if your inflation is 60 folds or if it's short, your end value is very close to the initial value.
Oleg,
Yeah.
one question. So in the first equation, you have a parameter epsilon in the zeta function, the argument of zeta function.
Yes.
But in the second equation, there is no dependence on the epsilon, explicit dependence on the epsilons. So what's happening to epsilon?
Yeah, so this epsilon is a fixed small parameter. It's much
Yes.
smaller than 1. And
Yes.
then it turns out that if you derive the equations of motion, epsilon disappears. So it's not a
Okay.
physical parameter, and so it doesn't appear in physical quantities. This was shown already by Starobinsky.
Okay.
So formally, everything works if epsilon is much smaller than 1. Again, if you do everything properly, you find that it doesn't appear in physical quantities.
Okay.
Okay. Yeah, good. So I've been talking about the field value. Okay, so the field value is not exactly particles. So it's some condensate of long wavelength modes. So effectively, you get some vacuum expectation value within a Hubble patch. So within a Hubble patch, this field is almost constant. But still, this is not particles. So during inflation, you cannot really talk about particles when you talk about this field phi. But inflation ends at some point, and this condensate starts evolving after inflation. So you have a radiation domination expansion or matter dominated expansion. And given a background, you can check how the condensate evolves in time. And eventually, this condensate starts oscillating because the field phi has a mass, has a small mass. So eventually, this classical force on the condensate becomes significant, and it starts oscillating. And you can interpret a collection. So you can interpret an oscillating condensate as a collection of non-relativistic particles. And that happens when the Hubble rate becomes comparable to the particle mass. So it's the same thing as what happens to the inflaton. If you have a m squared phi squared potential for inflation, you can interpret the inflaton field as a collection of non-relativistic inflaton quanta. So that works very well. So the same thing happens here. When the Hubble rate becomes comparable to the mass, you get just a collection of non-relativistic particles. And so you can therefore compute the particle abundance according to the usual formula. So you take the number density and divide it by the entropy density of the standard model. And then you get this quantity y, which gives you basically the ratio of the dark matter or dark relic particle number over the photon particle number up to order 1 coefficients. And so you can compute this quantity because we know what is n. I've shown you an expression in the Bogoliubov formalism, but you can compute this quantity also using the Starobinsky formalism. And what you find is this result. So the particle abundance is given by the condensate squared over the mass, the square root of mass on the Planck scale. And since the condensate is huge during inflation, so it's at least 0.4 to the Hubble rate. Maybe it's much, much larger. We don't know because it depends on the initial conditions. It could be as large as the Planck scale, okay, but certainly not below the Hubble rate. And so if you plug in the numbers, you find that the particle abundance produced by inflation is so huge that only particles with sub-electron volt masses are allowed if they are stable. Okay, otherwise we would have too many dark relics. So again, the statement is the following. So suppose you have a stable scalar field with mass m, and I compute its relic abundance. And what I find is that the abundance of this field is so large that it has to be super light to be consistent with the abundance of dark matter. Okay, and this production mechanism is entirely due to gravity, due to de Sitter fluctuations. So the main player here is the size of the condensate. Now, if inflation is followed by a long period of matter domination, the formula is different. But fundamentally, the result is similar. So in order to be consistent with the observed dark matter abundance, you have to dilute the number density of dark particles. And the dilution factor is here denoted by delta, and delta is defined here as the square root of the ratio of the Hubble rate at the end of inflation and the Hubble rate at reheating. This is the same as the ratio of two temperatures, one in case of the instant reheating. So if you convert immediately all the energy density into radiation over the true reheating temperature, okay, because reheating takes time, and so the real reheating temperature is always much, much lower than the instant reheating temperature. And so this ratio is very large, and it corresponds to a dilution factor. And so the statement here is the following. If you want the relic abundance of your produced particles to be consistent with the relic abundance of dark matter, or to be below it, your reheating temperature has to be extremely low. So it has to be below GeV. So this delta factor is very, very, very large, maybe 10 to the 14, 10 to the 15 10 to the 15. It appears in the denominator and it dilutes the produced relic abundance. So in both cases, you have extremely strong constraints. So if you have particles which have no couplings to anything, it's a scalar which just has a mass, and then you find that gravity is so efficient in particle production that it overproduces particles by many, many orders of magnitude. So you have to do something about it. And one is you can assume that the mass is really tiny, so something like an axion would work. Sub-electron volt masses are okay. Or if masses are different and you use matter domination, then you have to impose the condition that the reheating temperature is really tiny. So in that case, yes.
So question is, so for non-zero pi bar, so this corresponds to, this is not the case of the Bunch-Davis vacuum, right? So if phi bar is not zero, then the when you apply the A in the sorry, A into zero in vacuum, it's not zero. Is that right?
Yes.
So okay. Mm.
Yes. So this result is much it's much more general than the Bunch-Davis,
Mm.
but it includes Bunch-Davis as a special
Okay.
case. So you see, in the Bunch-Davis case, which is the standard Bogoliubov approach, this phi bar takes a specific value,
Mm.
which is given by the Hubble rate to the fourth divided by the mass squared, because this is the asymptotic
Mm.
value in the Bogoliubov approach.
Mm. Mm.
Okay, so it has a
Okay.
specific value. And
Mm.
here, I'm not assuming anything about the Bunch-Davis vacuum.
Mm.
I'm just saying
Mm.
that I know that there is a lower bound on this guy.
Mm.
Okay, and this phi bar cannot be below the Hubble rate.
Right.
If I use Bunch-Davis, in fact, phi bar will be much, much above this
Mm-hmm.
value,
Mm.
because you can see it. So basically, phi will be h squared over m,
Mm.
h squared over m. So it's h
Mm.
times h over m, and h over m is a huge number. So
Mm.
in fact, in the Bunch-Davis case, you get a much larger
Mm.
result. But like I said, it's physically, you cannot really justify it. So the best you can do is that you leave the condensate as a free parameter, which has a lower value. And the lower value is there because you cannot suppress quantum fluctuations. And therefore,
Right.
the lower value is the Hubble rate.
Mm. Okay, thank you.
Yep. Okay, so, and then, yeah, and then this is done in the simplest case on the for the case of non-minimally coupled, or for the minimally coupled scalar which has no self-interactions. But in fact, in this paper with my student, we generalized these formulas to a more general case where you can include weak self-coupling of the scalar field. You can include small non-minimal coupling to gravity and also general initial conditions. And you find this universal result. So the particle abundance scales always as the condensate of the scalar field squared at the end of inflation divided by some effective mass. And the effective mass is either the bare mass for a free scalar or sort of induced mass, which is the coupling times the vacuum expectation value squared after inflation. So for a self-interacting scalar, the induced mass is proportional to the self-coupling. So this thing will change. And then there is also a factor, which is always 1 for radiation domination. So this power gamma is 0 in the case of radiation domination. So this factor is not there. But in case of matter domination, this gamma is a half. And this factor can be extremely significant because it can give you a very large dilution. So if the Hubble rate during reheating is very, very, very small, it can be below the effective mass. So you would get a small number here, the square root of a small number. So effectively, this allows you to dilute the relics. So you produce a lot of relics immediately after inflation, but if reheating happens at very late times, this gives you a small number, and therefore you can make this abundance consistent with observations. But what is surprising, at least as it was surprising to me, that all of the cases can be described by this simple scaling.
Mm. One question.
Yep.
So here you are talking, the example was about scalar particle production during the inflation, and then what happens to the fermion production?
Yes, very good. This is also my question.
Okay.
What has been done, and I think it
Mm.
was done also, so it started with the work of Parker in the 70s. So he
Okay.
considered fermion production due to an expanding background, not inflation necessarily,
Mm.
but just some expanding background.
Mm.
And people revisited it and redid the calculations. Also, our group did it, and the result is that if you just take a fermion of a given mass
Mm.
and perform the same exercise as I did in this talk, you find
Mm.
that the production is suppressed, and it is suppressed by the mass of the particle.
Mm.
And the reason for it is that fermions are conformal,
Mm.
they up to the mass. So
Mm.
scalars are not conformal unless you go to the conformal limit. So the
Mm.
production is always there. But fermions are conformal, and the conformal symmetry breaking is encoded in the mass. And
Mm.
so if the mass is small, the effect goes away. But in
Mm.
this formula, you see the mass is small, the effect is huge. Okay,
Mm.
the mass appears in the denominator. And so what people normally would say is that fermion production is suppressed because the fermion mass is not large. Okay,
Mm.
and this is the simple answer, but it's not the correct one. The correct answer, I will tell you maybe in 2 months, the exact answer,
Okay.
but I can give you a brief recap of what I'm doing now. Basically, the thing is the following. The fermion mass is not a fixed parameter, even in the standard
Mm.
model.
Mm.
In the standard model, there is no mass for fermions. It just
Mm.
doesn't exist. What you have instead is a fermion bilinear coupled to the Higgs.
That's right.
Yes, and so everything depends on how the Higgs behaves.
Mm.
Of course, now we know that the Higgs is at the minimum of the potential, so we get a fixed mass. But during inflation, the story is completely different. The
Mm.
Higgs experiences the random walk like this.
Mm. Mm.
So its expectation value is huge. It's at least the Hubble rate.
Mm.
Actually, it's much larger than the Hubble rate. You can prove that
Mm.
because the self-coupling of the Higgs is known. So the expectation value of the Higgs field is huge. And the Higgs field couples to fermions. So it creates a huge effective mass.
Mm.
So in fact, fermions are produced uh, quite efficiently, even during inflation.
I see.
Not as efficiently as the scalars, but quite efficiently. And the exact
Mm.
number we're computing now, but I can tell you that it's large.
Okay. I look forward to your new paper.
Thank you. Hopefully it will be done soon enough.
Okay.
Yes. So, okay. Uh, it's been less than an hour. Okay, so I will soon finish the first part of my talk. So we still have time, right?
Yes.
Okay. Yeah, I think this format is good that you should interrupt me and we should discuss so that the talk is not too boring. Okay, so what I have talked about is purely classical gravity. So classical gravity is just a classical expanding background, as in textbooks. But this is not all, right? We know that uh, quantum gravity is important because classical gravity is simply inconsistent at high energies. And after inflation ends, quantum gravity becomes important in terms of particle production effects. So quantum gravity is believed to induce all gauge invariant operators with unknown coefficients. So the coefficients depend on the UV completion of your gravity theory. So in particular, quantum gravity couples the inflaton sector to everything else, and in particular, dark matter or dark relics. After inflation, the inflaton field value becomes smaller than the than the Planck scale. So you can use effective field theory expansion in terms of the inflaton field. If it's just a bit smaller than the Planck scale, you can use this phi over m Planck expansion. And so you get many operators, but among them you would get dimension 6 operators of this type that couple the inflaton to dark matter, dimension 8, dimension 10, and all of that. And the point is that since phi is not much smaller than the Planck scale, it is smaller, but not hugely smaller. So the suppression is not very significant. So in fact, all of these operators are important, and they can produce particles and can produce all of the dark matter. And the way it works is that phi starts oscillating in a, say, quadratic potential, maybe quartic potential, and it creates an effective oscillating mass for the scalar field. So it's S squared times some oscillating background. And so naturally it leads to particle production. And this mechanism is also very efficient. And here is an example how you can compute it perturbatively. So let me give you a simple example. Suppose I couple the inflaton to the Higgs or to some other scalar with some Higgs portal coupling. What you do next is that you expand the classical inflaton field in terms of the harmonics, because it's a periodic field, so we have oscillations, and so we can expand in harmonics, and then we can compute the transition from 0 Higgs particles in the initial state to 2 Higgs particles in the final state with given momenta. And the way it's done is just like what we do when we compute Feynman diagrams. So we take the interaction term, plug it between the final and initial state, integrate, and we get an expression something like this. This is what we see in Feynman diagrams as well. And the amplitude is proportional, obviously, to the Higgs portal coupling. It enforces also three-dimensional momentum conservation because you produce particles out of the vacuum back to back. But also it contains a delta function of the particle, the final state particle energy minus the oscillation frequency. So basically the particles take the energy from the oscillating field and they become real. Okay, so if the frequency is high enough, it can produce particles. And then given this amplitude, one can compute the reaction rate. One sums over all of the harmonics, integrates over the phase space, and one gets something like this. So this is a purely perturbative result, very simple, and it doesn't take into account collective effects, resonances, and so on. But for many purposes, it actually works. Now, if you have a more sophisticated system, so if this coupling lambda phi h is not too small, and not too small, I mean, here is an example with lambda phi h of order 10 to minus 4. For cosmological systems, this is a very large coupling. So what you find in this case is that this particle production process becomes really violent. You have Bose enhancement, you have resonances, and particle production becomes very efficient. And it back reacts on the inflaton background, actually destroys it, and the system reaches some kind of quasi-equilibrium. That's what is shown here. So we have taken the Higgs self-coupling to be 0 for simplicity, the Higgs portal coupling of order 10 to minus 4, and the inflaton here is heavy, and its mass is given in Planck units. So this is time, and this is the energy fraction carried by a particular particle. So the blue line is the inflaton. So initially, the inflaton carries all of the energy, and then it produces the Higgses or the scalar in this yellow line. So the production is quite explosive. So you go from 0 to 10% almost immediately. And then the inflaton background starts interacting with the produced particles, and they actually equilibrate. And so at late times, you have the fraction carried by the inflaton is a constant. So you have a complicated system. So this can also happen immediately after inflation. And what has happened in the past, we don't know. Now, the same consideration. So here I've taken a renormalizable coupling between the inflaton and some scalar, but the same considerations apply to higher dimensional operators, in particular to the inflaton coupled to dark matter. So you can, if this coefficient, so the Wilson coefficient of this operator is small, you can compute particle production perturbatively, as I did earlier. If it's not too small, then you have to take into account collective effects, resonances, rescattering, turbulence. You can put this operator on the lattice and compute the effects, which we have also done. And we find that the effect is very, very important, very large. So you produce a huge number of particles. What is important here is that, let me reiterate, is that gravity is not classical at high energies, and this is a known fact. So you cannot really mock up the physics of the early universe with a one graviton exchange. One graviton exchange is a tiny subset of diagrams, but the physics at the high energy scales is non-perturbative, and we have no idea whether one graviton exchange gives you any information at all. But people often do that, okay? So what we actually need is we need a UV complete theory of gravity, for instance, string theory. And in string theory, you can compute couplings between the inflaton and any other field. For instance, you can compute the endpoint function in string theory. And you know the Wilson, in that case, you would know the size of the Wilson coefficient of this operator. So in principle, in quantum gravity, this is computable, but we don't know which specific theory is realized. So therefore, all we can do is parameterize effects of such operators in terms of Wilson coefficients. And so what I wanted to emphasize is that we have a set of high dimensional operators suppressed by the Planck scale, but one can show that all of them can produce all of the dark matter. You don't need any other mechanism. All you need is a Planck suppressed coupling between the inflaton and the dark matter. And then even with the very, very small values of such coefficients, maybe 10 to minus 8, or maybe even smaller, you can produce all of the dark matter. So you don't need any other mechanism. You can do the same thing with fermions. As I mentioned before, the fermion production is much less efficient, but still is efficient enough to produce all of the dark matter. So for fermions, the lowest order operator is dimension 5. So you have a inflaton squared coupling to a fermion bilinear. And you can parameterize effects of this operator in terms of the Wilson coefficient C. And what you can do, you can compute, for instance, particle abundance due to inflaton oscillations produced by this operator. And the result is given here. So the particle abundance is basically C squared times some ratio of masses. And this number is large because you have the Planck scale, the Hubble rate. So in general, you produce a very large abundance of dark relics, but you can dilute them if reheating happens at late times. So what is surprising to us when we did this calculation, we found that this one gravity-induced operator can produce viable cold KV sterile dark matter. So the coefficient of this operator is something like 0.1, is still below 1, but not too small. This mechanism produces KV sterile neutrino dark matter. And actually you can show that it's cold because the energy of the neutrinos is given by the inflaton mass, and it redshifts. And so at the time of structure formation, these neutrinos are non-relativistic. So even if they weigh as little as a keV. So this is very interesting, and it provides an irreducible background for any sterile neutrino production mechanism, in particular for Doddelson-Widrow. So people say that Doddelson-Widrow is ruled out, but Doddelson-Widrow start at 0 particle abundance at reheating. But gravity shows that this is not a reasonable assumption. So you must start with some non-zero particle abundance because you cannot switch off gravity. And so quantum gravity can produce all of the neutrinos you need. So this is one point. But the main point of this part of the talk is that all non-thermal dark matter models, or all Friesian models, suffer from the gravitational background. So gravitational production background, which you cannot predict because you don't know exactly the Wilson coefficients of quantum gravity induced operators. Also, we don't know, if we go back to the first part of my talk, we don't know how long inflation has lasted, and the particle abundance depends on the duration of inflation. It depends on the initial pre-inflationary initial conditions of your scalar fields. So there are many unknowns. So in fact, we don't know how many particles inflation and preheating actually produce. We can set a lower bound, but we cannot really have a solid prediction.
Right.
What we
So,
know is that this number is very large. Yes.
so because it does depend on this coupling, which is of course unknown, then I guess obviously there could be additional contributions in addition to the usual Friesian production from for star neutrinos, let's say Dawson-Widrow, right? But that also means that you can't necessarily rule out Dawson-Widrow because you have this additional background, because this additional background could be actually quite low, right? I mean, we just don't know
Yes.
whether it's low or high. Yeah.
That's right. So basically, this is a correct statement. What you can do here is that you see the reason why Dawson-Widrow is ruled out because it predicts a particular mixing angle between active and sterile neutrinos. And that means that sterile neutrinos decay and the decay rate is known. So you can look up in the sky and check whether this decay happens, and it turns out it doesn't happen, so the mechanism is ruled out. What is happening here is that you can set the mixing between active and sterile neutrinos effectively to 0. But because this production mechanism is independent of the mixing angle, you produce all of the neutrinos you need, and they decay very, very slowly. So you cannot rule out this mechanism. So indeed, you're right that it provides a background for Dawson-Widrow, but in fact, if you look at it, you don't need Dawson-Widrow. You can set the mixing angle to be very small so that Dawson-Widrow is inefficient, and it doesn't lead to fast sterile neutrino decay.
Right. They're just independent processes, basically.
Yes, that's right. Exactly. That's right. Yeah. So, sorry, just a second. Let me just grab some water. Yeah, so this is basically the end of this gravitational particle production thing, which motivates the second part of my talk, which will be probably briefer. Yeah, most likely. Maybe I will finish in half an hour or so. Right. So the bottom line of the first part of my talk is that gravitationally produced relics may be the end of the story, and very likely that they are the end of the story. It's a very simple, natural production mechanism. You don't need any additional ingredients. This happens under very general circumstances. So maybe the dark matter that we see is produced gravitationally. Now, this is a sort of a depressing viewpoint. And now the question is, can we get rid of this? So under what circumstances can we suppress gravitational particle production? And the simplest way to do it is as follows. So we allow efficient gravitational particle production in the early universe, which happens at the end of inflation and shortly afterwards. But the most efficient mechanism is operative immediately after inflation. So you produce lots of relativistic particles. You produce too many relativistic particles. And the energy density scales as 1 over scale factor to the 4th, whereas the inflaton energy density in case of a non-relativistic inflaton scales as 1 over the volume. So the ratio of the two goes to 0 at large scale factors. Okay, so if we wait long enough, if the energy density of the universe is dominated by an oscillating inflaton for a long, long time, it dilutes away the energy density of our relativistic relics. And so at low reheating temperatures, basically, you start with 0 initial abundance of dark particles. Okay, and so the simplest way out of this gravitational production problem is to have a low reheating temperature. Maybe as low as GeV, maybe as a TeV, or maybe as 5 MeV. So again, it depends on further details. Now, suppose that we take this scenario seriously and suppose that the reheating temperature is low. So now we have a real possibility that the reheating temperature is in fact below the dark matter mass. Okay, normally in traditional models, you assume that the reheating temperature is huge, maybe 10 to the 10, 10 to the 14 GeV, and so the dark matter mass would always be below that. But in this case, it can easily be below, so the reheating temperature can easily be below the dark matter mass. So what do you do then? So in that case, you can still have a freeze-in, but this freeze-in has an interesting feature. Okay, so suppose we have a thermal bath of standard model particles with a low temperature. Here is the Boltzmann distribution of standard model particles with a given energy. So this is the standard Boltzmann distribution. And most of the standard model particles don't have enough energy to produce dark matter because dark matter is heavy. Okay, so if you annihilate 2 dark matter quanta into a dark matter, often, so for most particles, this process does not take place due to kinematics. So you have to pick up the most energetic particles from the bath sitting at the Boltzmann tail, and only those have enough energy to produce dark matter. So this production process is naturally suppressed due to the Boltzmann factor, not due to the coupling. So this coupling between the standard model and dark matter can be order 1, but the process is still exponentially suppressed. So this is the idea behind freeze-in and stronger coupling. Okay, let me flash the sort of a general view of dark matter models, the theory space of dark matter models. So if we have some generic coupling in the model, if this coupling is large, so we typically have freeze out. Yeah? Dark matter thermalizes and then freezes out. And that only works for sufficiently large couplings. At very small couplings, we can have traditional freeze in, And normally you require really a tiny coupling of order 10 to minus 12 or 11. And that assumes that the reheating temperature is very large. But then we find that there is really a desert in between. So between 10 to minus 12 and 1, there is nothing going on. So the natural question is, what's happening there? And this is something that I'll try to answer. Okay, so let me say a few words about the reheating temperature. So what do we actually know about the reheating temperature? Cosmologically, all we know is that the temperature has to be above 4 MeV because we know that the BBN is successful, so it's perfectly consistent with the data. So there was a stage in the early universe where the standard model radiation dominated, and you can compute the Hubble rate during this time, and the Hubble rate is consistent with nuclear synthesis. Therefore, there is this constraint which you cannot avoid. But there are no other constraints. So we don't know whether the temperature was high. Normally, it's assumed that the reheating temperature is high because, okay, just traditionally, if you take any textbook, you find that people just assume that. But this assumption is not based on physics. It's just a simplifying assumption. And if we look at this number is very small. So why should we assume that reheating temperature was ever high? So now the program is to actually base our analysis just on observations, on physics, rather than prejudice, and reanalyze all the typical simplest extensions of the standard model in the framework of low reheating temperature. So we can take the Higgs portal, dark matter, Z prime extension, sterile neutrinos, and so on. And what we find in all of these cases is that Friesen actually has direct detection signatures, and also it has collider signatures. So let me give you the simplest example. The simplest example is the Higgs portal dark matter, which is due to Silveira and Z. So they wrote down the model in the 80s. But we have reanalyzed it in the framework of Friesen and stronger coupling. So in this case, we have a standard model thermal bath, and the main player is the Higgs. The Higgs particles annihilate and produce pairs of dark matter via the quartic vertex. Of course, you can include all of the diagrams, it's not hard, but the main player is this contact interaction. Then you solve the Boltzmann equation. It has the production term and the annihilation term. So in the Friesen regime, the production term dominates and the annihilation term is smaller. So in Friesen models, normally you neglect it. But there is a subtlety, which we will discuss later. So suppose we focus just on the Friesen regime. So we solve this equation. We compute the production rate first. And the production rate is proportional to the coupling squared, which appears here. And what is important is that it contains also the Boltzmann factor, which I alluded to before. So if the temperature is low, the reaction rate is suppressed by this factor. So it contains a mass over a small temperature in the exponential. So it's exponential of minus very large number. So the production rate is suppressed due to that, not due to the coupling. And you can invert this equation and you solve the Boltzmann equation, and you find that the Higgs portal coupling that produces the right amount of dark matter is given by a tiny number times an exponentially large number. So if the mass of your dark matter is higher than the temperature, then this exponential factor is large, and it compensates the smallness of the prefactor. So you can easily have order 1 couplings while still having Friesen. So you can include the annihilation effects, and then you can prove that dark matter does not thermalize if the coupling is not too large. So the production rate is different from the annihilation rate. And here is the famous plot for a singlet scalar dark matter. So you take this potential, okay, just the mass term and the interaction term, and then you plot the allowed couplings versus the dark matter mass, and this purple line gives you the right relic abundance. So that's a pretty well-known figure, which has been reproduced by many groups. And the dip has to do with the Higgs resonance. But the bottom line here is that almost the entire parameter space is ruled out. So at low energies or at low masses, you have invisible Higgs decay into dark matter. So this parameter space is ruled out by the LHC. You go to higher masses, then you get a large direct detection rates. So what remains is just the tip of the resonance. It's below the xenon and LZ, direct detection bound. And you also have a high mass tail. So above 3 TeV, this Higgs portal dark matter is still consistent with observations, but you're quite squeezed. And basically the parameter space up to 3 TeV is ruled out. Now, let's do the same exercise for freezing at stronger coupling. So now we treat the reheating temperature as a free parameter, which it is, because we don't know what it is. Normally people assume it to be high, but let's be more honest about it and just vary it along with the mass and the coupling. And so what we find is the following picture. So each colored line gives you the right relic abundance due to freeze-in at stronger coupling. So these colored lines are marked by the reheating temperature in GeV. So here we have 300 GeV. Here we have 200 MeV. So essentially, the entire plane is filled with freezing models with varying reheating temperatures. So every point is a viable dark matter model. Now, some bits of the colored lines are ruled out by observations. So in particular, LHC rules out a significant chunk at low masses and substantial couplings. Direct detection also rules out some of the freeze-in lines. But what is exciting is that such freeze-in models can still be probed by direct detection. So the dashed line gives you the neutrino floor or the neutrino fog. So the parameter space above the neutrino fog will be probed by future direct detection experiments. So xenon or Darwin and so on. So we can probe all of this parameter space. At low masses, the LHC and FCC will probe invisible Higgs decay. So this parameter space will also be probed. So what it means is that there are still interesting prospects for direct dark matter detection in the simplest possible model. So the simplest possible model is not ruled out. It's just people make strong assumptions, but we relax such assumptions. We find that this model is perfectly observable, and maybe in the next 10 years we'll find something. And it also, this plot also shows how you go from freeze in to freeze out continuously. So suppose we take the 300 GeV line, and at small couplings of order 10 to minus 4 or 10 to minus 5, we have perfect freeze in. So we produce particles and they don't back react. And this remains true until you increase the coupling up to almost order 1, maybe 10 to minus 1 or order 1. And in this case, you find that the produced dark matter particles started annihilating efficiently. And And in fact, the system thermalizes at significant couplings, and what we end up with is the thermal relic abundance line. So the freeze-in line merges continuously with the thermal freeze-out. And you cannot go above the thermal freeze-out line. So above the purple line, this space remains ruled out. But below the purple line, all the space is filled with viable models, which can be probed. So again, let me emphasize that I'm not inventing a new model here. I'm taking a very old model from the 80s, and I'm just treating the reheating temperature as a free parameter, which it is. Okay, so now maybe a few words about very low reheating temperature. So here in this plot, I showed the reheating temperatures down to 200 MeV, but on the previous, so the actual physical constraint on the reheating temperature is something like 4 MeV. Okay, so a natural question is what happens at very low reheating temperatures? And this question is pretty hard because at low reheating temperatures, the standard model thermal bath is very different. So we don't have elementary quarks anymore. Instead, we have a thermal bath of pions and kaons and leptons. And in this case, we need to compute dark matter production due to annihilation of hadrons and leptons. Leptons are, of course, very easy to treat, but hadrons are very difficult. So what do you do then? What we did is the following trick. So what we start with is a thermal standard model state. So for instance, 2 pions or 2 kaons. And what we need is we need to compute the annihilation cross-section or annihilation rate or reaction rate for a standard model thermal state into the Higgs intermediate state, which then splits into 2 dark matter particles. Okay, so this process is always mediated by the virtual Higgs. And the dark matter in the final state is completely non-thermal because this is freeze-in. So it has some unknown distribution, non-relativistic distribution, but certainly is not thermal. Now, if you write down the formal expression for this reaction rate, you can show that it equals exactly the reaction rate for thermal dark matter into the Higgs intermediate state and which splits into the standard model final state with some unknown distribution. So this relation is formal. It doesn't require dark matter to be thermal, but the reaction rate is equivalent to that of thermal dark matter. Okay, as long as you ignore quantum statistical factors, which you can at lower temperatures, you find that these 2 rates are equal. And this expression is much easier to handle because what you can do is that you can cut this diagram in half and compute thermal dark matter annihilation rate into the Higgses. It's a trivial calculation. And multiply it by the Higgs decay rate into the standard model particles. Okay, and the standard model particles, of course, include leptons and so on. But most importantly, they include the hadronic final states. So the Higgs can decay into pions and kaons and so on. And this decay rate has been computed non-perturbatively using chiral perturbation theory, dispersion relations, and so on. So this is something that people have done for all Higgs masses. And the end result is given here. So if you want to compute the reaction rate for a standard model particle annihilation into dark matter, you need to compute this integral, which contains thermodynamic factors, the dark matter annihilation amplitude, which is very simple, but the non-trivial factor is here. So you need the Higgs decay rate into hadrons for any Higgs mass. Okay, but this has been done by people who do hadronic physics. And so the end result is here. And this is the Higgs portal coupling versus the dark matter mass. And you find that at masses above 100 MeV, you have the usual dependence of the coupling on the mass, which is exponential. But at low masses, the dependence is completely different. And so in any case, this parameter space is perfectly viable, and the reheating temperature here ranges from 80 MeV at the bottom to 4 MeV at the top. So 4 MeV is ruled out by the LHC, 10 MeV is almost ruled out, but something like 20 MeV is perfectly allowed and will be probed by high luminosity LHC and FCC. And the dominant production mode for dark matter in this case is pion annihilation into dark matter. Okay, so let me now say a few words about some assumptions that play a role in this framework of reheating at low temperatures. So what I have assumed so far is that the temperature of the standard model bath has never been very high. Okay? I referred to the highest temperature as the reheating temperature, but in reality, the maximal temperature of the standard model bath is different from the reheating temperature. So what is the relation between the two? So in fact, we don't know what is the relation in general. If you take any textbook, for instance, Kolb Turner, you find this formula. So the maximal temperature of the standard model bath is given by this expression. And if you plug in the numbers, you find that the maximal temperature is very large. So what is assumed here? Well, what people normally assume is that the inflaton decays into the standard model directly, which is a natural assumption, but is not necessarily the case. So if the inflaton decays directly into the standard model particles, then this expression is correct. And here is how it works. So this is the energy density versus the scale factor. You start with the inflaton, and the inflaton dominates the energy density for a long time, but it decays into the standard model fields immediately after inflation. So you start with a zero abundance of the standard model fields, and you produce the standard model fields via the inflaton decay. So the energy density in the standard model goes from 0 to some maximal value. And if you take the fourth root of this energy density, you get the temperature, because the standard model thermalizes very quickly. So even though it gives you a subdominant component in the energy density, it still forms a thermal bath. So you can compute the temperature simply by taking the fourth root of this value. And then you solve the evolution equations, and you find that the energy density of the standard model bath decreases over time, and but it decreases rather slowly, whereas the energy density of the inflaton decreases faster, as 1 over the volume. And so eventually at late times, the standard model overtakes the inflaton and starts dominating. And that's when reheating happens. But you see, this reheating temperature is typically lower than the maximal temperature of the standard model bath. Now, again, this hinges on the assumption that the inflaton directly decays into the standard model fields. Let's look critically at this assumption in the framework of freeze-in. So what are the basic assumptions of the freeze-in paradigm? Well, the assumption is that after inflation, the inflaton field decays only into the standard model fields, and it does not decay into this dark sector, because that's not how freezing works. Okay, so freezing works due to the existence of the standard model thermal bath, which generates dark matter via tiny coupling. So this usual traditional freezing approach requires two tiny couplings. First of all, you require a tiny coupling of the inflaton to the dark sector so that you forbid this process. And the second tiny coupling is the coupling between the standard model and the dark sector. So in fact, there is a fine-tuning squared, unless you can, of course, justify it with some symmetry. So let's use the same logic and make a logical extension. So if we allow for this possibility, we should certainly allow for another possibility, that the inflaton does not decay into the standard model, again for some symmetry reason, and decays entirely into the dark sector. And in this case, the relation between the maximal temperature of the standard model bath and the reheating temperature changes completely. So here is a general situation. Suppose that the standard model thermal bath was created by some spectator. So the energy density of the standard model is given by rho, and chi is some spectator which has decayed into the standard model particles with some fixed decay rate, gamma chi. So the evolution of the standard model energy density is given by this equation. So it's fed by the energy density of the chi field, which is unknown. And then we also assume that the Hubble rate scales as some power of the scale factor, and the energy density of this spectator scales as, again, with some scaling with a fixed n. So, and this set of equations can be solved in a generic case. We don't know how the standard model fields were produced, so we don't know what is chi, but we can solve this system, and we find this solution. So the energy density of the standard model fields is given at late times by this expression, some constants, but the most important factor here is that is 1 over a to the power n minus m. And n minus m are just some input parameters. So what it tells you is that the energy density of the standard model fields before reheating can increase when n is below m, can be constant when n equals m, or can decrease, which is the traditional case, when n is larger than m. All of these cases are allowed in general. So, and fundamentally, none of them is preferred. We don't know anything. We don't know how the standard model quanta were produced. So let me give you the simplest possible example. Suppose that the inflaton decays into right-handed neutrinos, which could be quite heavy. Maybe TeV, maybe heavier, maybe lighter. I don't care at the moment. And this decay can be enforced by symmetry. So we can forbid phi decay into the standard model if phi carries some non-trivial quantum number, for instance, a lepton quantum number. So it decays entirely into leptons, but cannot decay into the standard model. So then we produce a subdominant component of right-handed neutrinos, and the subdominant component decays into the standard model. So it's a two-way process, or two-stage process. And here is the plot of the energy density versus the scale factor. So the energy density is dominated by the inflaton. Its decay produces a subdominant component of the right-handed neutrinos, and the right-handed neutrinos produce the standard model. And if you plug in the scaling, so for right-handed neutrinos, you know n and m. So for this system, you know n and m. You compute this quantity, and you find that n equals m always. And you find that the energy density in the standard model is actually flat. So it's time independent. And therefore, if you take a fourth root of that, if you compute the temperature, it is also flat. So the temperature of the standard model thermal bath is actually flat for cosmologically long periods. And therefore, the reheating temperature is basically the same as the maximal temperature, which justifies my previous assumption. Now, yeah, you can, as I mentioned before, you can extend the simplest Higgs portal model of dark matter to other possibilities. So you can look at Z prime extensions of the standard model where dark matter is a Dirac or Majorana fermion that couples to the Z prime. Again, you can explore parameter space. You can also play this game with a singlet extension of the standard model, which couples to the right-handed neutrinos, and the right-handed neutrinos would play the role of dark matter. Again, you map out your parameter space. In all of the cases, you find that freeze-in at stronger coupling is observable. It leads to direct detection of dark matter and also to signatures at the LHC, in particular, invisible Higgs decay into dark matter. So the parameter space is already constrained, but it can be further constrained or discovered at the high luminosity upgrade or FCC. All right, so the answer to my question is the following. So again, let me go back to the theory space of dark matter models. At tiny couplings, we have traditional freeze-in. At large couplings, we have freeze-out. And as I showed on the previous slides, the space between these two extreme possibilities is filled by freeze-in and stronger coupling. So that's how you actually go from the FIMP to WIMP continuously. Okay, so this desert is not a desert, but a space of viable models with couplings which are not as small as 10 to minus 12 and not as large as 1. So the conclusion is that gravity is very efficient in particle production. You cannot really sweep it under the rug. You really need to look at it very carefully. Dark relics are normally overproduced during and after inflation. Non-thermal dark matter models are very sensitive to quantum gravity, so in particular to higher dimensional operators, which are generated by quantum gravitational effects. And therefore, the traditional freeze-in paradigm is problematic because it assumes a zero initial particle abundance, which is not realistic. And this motivates the possibility of freeze-in and stronger coupling, which has signatures both at the LHC and in direct detection. So I'll stop here. Thank you.
Great. Thank you for your presentation. Are there any more questions?
Oh, thank you very much. I think I have enough question. So that's very great, and thank you very much for your talks for almost 2 hours.
It's a pleasure. Thank you for intelligent
yeah,
questions. It was
yeah,
nice to discuss.
I see. For me, I'll study your talk file, and I can contact you when I have more questions.
Perfect.
Okay.
Sure.
Yeah.
Excellent. So should I send my talk?
Yeah, that'll be great to
Mhm.
Philip and to me. Yeah.
Yeah.
I mean,
I'll
yeah.
do that. Yes.
Okay.
Perfect.
Great. All right. If there are no more questions, let's just thank the speaker again. And
Yeah.
I'm sorry,
Thank you.
can I ask a question?
Yes, please. Yes.
Thank you. For the case of lower reheating temperature, is that what is the role of the reheating process? Because it seems that a standard model particles or dark matter can be already produced. So is it just for swiftly reducing the energy density or?
Yes, that's right. So the low reheating temperature allows you to dilute the relics
Mhm.
produced by inflation and after inflation. But the reheating process can be completely standard. So you couple the inflaton to the standard model, but only with a small coupling. So the inflaton naturally couples to many things with a small coupling.
Mhm.
In traditional models, it couples to itself with a small coupling. So the delayed reheating is not some model building.
Mhm.
It's just you introduce a small coupling, which is natural in the inflaton sector. Maybe you put in a coupling of order 10 to minus 10, maybe smaller. For in the context of freeze-in, it's not a surprise. And in the context of inflationary model building, also it's quite natural. So you have a small coupling between the inflaton and the standard model sector, and so reheating happens when the decay rate becomes comparable to the Hubble rate, and the decay rate is small, so naturally you have reheating at very low temperatures.
Mhm. Yeah, but you've already considered the gravitational interactions. So is it not enough to reduce the energy density?
No, but you need to generate the standard model fields. And I think my answer is that there are some claims in the literature, but I think they're not really substantiated. So I think gravitational reheating doesn't work. So I think it's partial. So gravitational reheating uh, is, is, is partially fine, but it's never complete. So you need to always let inflaton decay into the standard model fields at some point. So gravity can produce a lot of particles, but it cannot fully reheat the system. I think this is my view.
Oh, I see. Thank you.
Sure.
All right. Well, thank you for the talk.
Thank you.
Have a nice day.
Yep.
You too.
Mm.
Bye-bye.
Bye bye.